Welcome. This video will explain Ohm's law and give you a few examples of how it's used in circuit analysis. So to begin, Ohm's law is basically a comment about resistors, or a property of resistors, something like that. You'll remember hopefully that the symbol we use in a schematic for a resistor looks like this. At least if you're American. I understand that if you're European, it looks like a box, which I respect, but somehow doesn't seem nearly as exciting as this kind of squiggly line. Resistance, which is a property of resistors, is typically denoted, or often denoted, as R. It's measured in units of ohms, which are named after a famous German engineer who investigated the properties of resistors. And Ohm's law is given in a couple different forms. One looks like this: V is equal to I times R. So what this means, if I have a resistor and it's got some voltage across it, V, and it has some current through it, I, then the relationship between the voltage and the current is that the voltage is I times the resistance. We can manipulate this algebraically to also say that I is equal to V over R. So if I were to give you voltage and resistance, you could compute current. And sometimes, we don't do this that often, but sometimes our goal is to determine what a resistance is. And so if we can measure voltage and current, we can say that the resistance is the voltage over the current. So those are all examples of Ohm's law. And what I'd like to do now is a few examples that show you how to apply Ohm's law. And then we'll finish up by talking about how to compute power dissipation in a resistor. In fact, that's a point I should make now and we'll make again. Real-world resistors always dissipate power. Most of the time, a resistor is modeling some circuit element that turns electrical power into heat. We model light bulbs as, at least incandescent light bulbs, as resistors. And there, some of the energy actually gets turned into light, but typically resistors convert power into heat, or electrical power into heat. So to do an example, let's suppose that we have the following circuit. We have a voltage source which provides 120 volts, and that's connected to a resistor with a resistance of 144 ohms. The symbol for ohms is a capital omega. So we know that the voltage here is 120 volts. This models, in actually a very simplistic way, the connection between a light bulb, in this case we'll discover it's a 100-watt light bulb, and your wall outlet, which if you live in the United States is nominally 120 volts. Now, this example, in the spirit of complete and honest disclosure, I'm lying to you about this in the sense that the 120 volts that you are used to dealing with out of a wall socket is really an RMS value that accounts for the fact that the voltage is an AC voltage. But we'll ignore that for now, and when we actually do an example with AC voltages, you'll discover that the answers we get are exactly the same. That's the beauty of RMS values. But for now, just think of this as a voltage of 120 volts, a voltage source of 120 volts connected to a resistor of 144 ohms. And so we'll define a current here, and our goal is to find this current. Okay, now I'm going to work this very explicitly, and some of you might say, well, this is either obvious or kind of silly, but I want to do it to make sure that some fundamental concepts are clear. My experience teaching this material is that quite often these fundamental concepts can be somewhat confusing. So the first is this. This area, or this part of the wire that I'm outlining in green, is all part of one node in the circuit. A node is defined to be basically everything that's connected by just a wire. And because we assume wires are perfectly conducting, there's no voltage difference between any point, between any 2 points along this wire. So the voltage here is the same, or there's no voltage drop between here and here. Similarly, the bottom wire here also forms a node. And again, because we assume wires are perfectly conducting, there's no voltage drop between here and here. So what that means is if the voltage between this point and this point is set by the voltage source to 120 volts, that the voltage across the resistor, which you might think of as the voltage between this point and this point, is also 120 volts. And again, that's a consequence of the fact that ideal wires never have any voltage drop in them. Also, now that I've made sort of a mess of, well, actually, we'll wait to talk about the current for another example in just a minute. Okay, so I want to find the current. Well, according to Ohm's law, the current is the voltage across the resistor divided by the resistance. We've just said that the voltage across the resistor is 120 volts. That's this value right here. The resistance is 144 ohms. And so if I actually do this computation, which I'm having a hard time doing for some reason, I get then that the current is 0.83 amps. Okay? So Ohm's law again tells me that because I have a resistor with a resistance of 144 ohms, I put a voltage of 120 volts across it, this is what the current is. And the voltage source will make sure, again, it will do whatever it has to do to make sure that the voltage across the resistor is 120 volts. In this case, what the voltage source has to do to make that happen is supply a current of 0.3 amps. Okay, so that's pretty much computations of voltage and current. We can also find power in resistors. And so we'll use this same circuit to do that. You'll recall from the video on power or other sources, power is the current times the voltage. Okay, but we know in a resistor, the current is the voltage over the resistance. So I can write this as V over R. Okay, you can see I've taken this I and replaced it by this V over R times V, or I can simplify this as V squared over R. Okay, so in this example, my power is equal to 120 volts squared divided by 144 ohms. And when I compute this, this turns out to be 100 watts, which is good. That's what I started with. Now, this gives me power. This expression here gives me power in terms of the voltage across the resistor. I can also find power in terms of the current through the resistor. And I do that by starting with this expression, and rather than substituting in V over R for I can substitute in for V I times R. So I have power, whoops, don't know what happened there. I have power is I times V, but for a resistor, V is I times R. So the power is I squared R. Okay, so again, the power in my light bulb is I squared, which is 0.83 squared times 144. And I'll actually work that out and make sure I get the right answer, because it's always sort of nice when things work out. So I take 0.83 squared and multiply by 144 ohms. And to the accuracy of my calculation, this turns out to be 100. Okay, so that's 100 watts. And I've been very sloppy here. This should be amps, and this should be volts. Okay, so that pretty much concludes this video of Ohm's law. To review, we've talked about the fact that Ohm's law says that voltage is proportional, or the voltage across a resistor. In fact, we can draw a graph here where we draw current on one axis and voltage on the other axis. And we've said that the voltage is proportional to the current, and the proportionality constant is the resistance. So what this means is that the relationship between current and voltage of a resistor can be drawn with a straight line graph, and the slope of this line is the resistance R. This turns out to be useful. In fact, this is actually a very useful way of thinking about components and how to model them. This is called a, depending on who you talk to, an IV curve or a VI curve. I've seen both used. In fact, I end up using both on a fairly random basis. But the idea is it shows us the current and voltage characteristics of a resistor. These VI curves can be used to model what happens in nonlinear circuits, and it can actually be quite useful. So this concludes the presentation of Ohm's law.